stream network models, so extending spatial models to different sort of different ways of defining distance. And then also mixed in today is some concepts about detectability and estimating detection probabilities, which isn't something we've talked about. But interestingly, the only person whose project I think references detectability explicitly is one of the public health ones. I'm trying to remember which, who, I'm sorry that I remember who he's doing which project very well. Of y'all, I have many people, but one of you has like a aerial census data that seems higher quality than point count, like cluster sampling. And so anyway, there's some chance that people might be interested in detectability. So that's today, and then on Thursday, Jay will be talking about adaptive diffusive movement models. So I think that's sort of an interesting class of models where you can define models that are conditionally Gaussian. So the transition from time t to time t plus 1, has some error that's multivariate normal, but you can't necessarily define the joint likelihood of the whole process because the diffusion operator is not, when you invert it, it's not guaranteed to have certain properties. So it's sort of an interesting class of sort of non-separable, but kind of mildly non-separable model. So that's this week, and then next Tuesday, I'm doing the last lecture, which is basically just like a review, and it'll probably be more kind of discussion focused. So me trying to ask people about sort of what they might have picked up and use it as a chance to get feedback on what concept did and did not really stick. And then on Thursday, we're starting the presentations, obviously, Thursday of next week. Finals is on the following Wednesday. I won't be there for finals, but the recordings I'll use to grade. And I'll also need all of the written projects due on that Wednesday. So, I think that's the 6th maybe of June. Can anybody confirm if that's a Wednesday?
Make sure it was June 6th. Yes.
Yeah, okay, so I'll have the written projects due on that June 6th, and there's a description in the syllabus of what I'm expecting. I'll probably send out an email with more details about what I'm looking for in the presentations and in my written, submission. And those are most of the grade of the class. Okay, any questions before we get started today? Okay, so so today, stream networks and estimate detection probability. So interestingly, I think in fisheries at least, some of the biggest, my reading in the literature is that there's sort of a strong group of geostatisticians out of France, Petit Gas and Mathieu Wallet and others who have been doing these models for, since the 90s, kind of creaking and classical geostatistics on fisheries data sets. There's also a really strong tradition in North America of doing kriging, like block kriging and geostatistics on stream networks for inland, like river networks. So like Jay Verhoof, who's a student of Cressy Weichel, I believe, Chris Weichel, and Peterson and a bunch of others that have published in ZDFS a lot. So they often start out with like state agencies go out and do sampling along, this is my kind of favorite silly cartoon of a stream network. So you might have like, I don't know if any of you guys did, I guess Elizabeth, you probably know, freshwater fish better than anybody here, but so correct me if I'm wrong or if you think I'm missing the plot. But like you'll have these stream networks where it's like I think it's called a Huck1, where a stream network originates, and then when it joins other streams, it like if a Huck1 and a Huck2 meet, I think it stays a Huck2. But if a Huck2 and a Huck2 meet, it becomes a Huck3, so you get these like river order classifications that state agencies use. And if you look at a stream network, a lot of times like a Huck1, like no fish are gonna be able to swim in. So, you start like looking at a network with like Huck2s or Huck3s or whatever. And you might have sampling defined such that the samples are not too close because this, the state agency kind of, I think, historically would sample and then they would try to figure out what's the distance that the next sample is sort of independent. And so they would sample a good distance away and so they end up with these like equally spaced samples, which is kind of the worst for estimating a spatial model. But, and so you might end up having, sampling at a bunch of these locations, and then I'm in this network also adding a circle at each confluence of different rivers, or the join of any different, of two different streams. So in this case, I guess we've got 11 dots. So you could imagine that either you have sampling of all 11 of these, or you could kind of think of this as like kind of similar to the SPDE approach, where you've got some of these where you don't actually have data. So in reality, maybe you just have sampling at these, and then every stream join, you don't actually have data, but you want to add a node there for reasons that will hopefully become more clear. Okay, so that's the design that people often do. And also, I think historically there's sort of a big concern, justifiably, with estimating detection probability. So I don't think, my understanding is that Beth Gardner still has not had the time, and SAS hasn't dedicated the resources to allow her to teach like an occupancy modeling class. So I don't think anybody at SAS is really covering kind of site occupancy, site abundance models. And who here, I guess Skalski still probably teaches Tagger capture. Do people, who here is taking the Tagger capture class?
Beth might have covered that in her Bayesian class.
Okay.
Or
Yeah.
I don't know if I feel like she might have touched on it at some point.
I bet she did. Yeah, I remember talking with her, and she was saying that Bayesian one, she was targeting applied problems that mattered.
Andre covers tag recapture in one of his lectures, but it's not a full quarter. It's just one lecture.
Got it. Cool. Well, I mean, I don't know. I already put this up on the board. I've only got maybe 11 slides today, so it's not, it's not super long to blitz through the lecture material. But does anybody want to say their sort of feeling about estimating detectability from Tagger capture? What's sort of the common thread? This is sort of my summary that I've already put up, but feel free to.
I mean, you try and have some period of short-term sampling when you think that the population is closed, or that occupancy isn't changing, and so you do repeated sampling so you can try and get at
Totally.
your detection probability.
Yeah, exactly. Yeah, right. And I mean that's sort of how I come down on this too, is that there's this whole there's the Royal and D'Orazio have a textbook called hierarchical models, and their extensions in R or something like that, which is awesome. And there's a whole textbook full of kind of one-off cases about estimating detectability. Charlton, I was trying to bring up so one of you HME people had two different data sets, one of which I think was an aerial census, and another that was a cluster sampling. Is that?
I think that's Nat.
I was trying to think of a public health example of where detectability might matter, and one case I think is these situations where a nation might have a census of some process. But it's at kind of a coarse scale. And then you might also have sort of sampling at a fine scale where you might miss people. And so these kind of cases of how to estimate detectability and also occur at public health. But let's see, so a lot of these different ways of estimating detectability end up coming down to some time scale and some spatial scale at which you can assume population closure. So like a site occupancy model, you go into a site when it's occupied or unoccupied and you sample it, and you assume that it can't change its state between multiple replicated samples of that population. An individual, like a tag recapture study, is sort of a special case of that, where once you tag an individual, that individual is sort of, it's not demographically closed, but it can only go one way. If you tag it, it will die, but it will never come back to life with the same tag. So that's sort of useful information about this sort of kind of type of closure. Okay. So there's a bunch of different ways to do estimated detectability, and one of them is triple pass depletion sampling. So in a triple pass depletion sampling design, as I understand it, you go out to a stream and you put out, a net, a gill net at one part, and then maybe like 100 feet up from that, you put another gill net down, so that you know that the fish within that stream segment are unable to leave. That you assume that you eliminate movement, and you do sampling over a very short period, so you assume that they're not dying. And then you also do it over a small enough area that you assume that individuals are kind of mixing equally, or that you can sample randomly with respect to the individuals in there. And so if you've got that design, I'm going to say like the probability that a given individual is detected, so some random event, random variable representing the event, that a detection occurs in pass 1, where Z indicates the pass. The probability of detecting in the first pass each individual is equal to P, this detection probability, which obviously has to range from 0 to 1. The probability that you miss it in the first pass and then capture it in the second pass is equal to P times 1 minus P. And then finally, that you capture it in the third pass, given that you missed it in the first 2 passes, is equal to P times 1 minus P squared. So those are just assumptions that each, you could derive these formula. I mean, maybe they're intuitive, maybe they're not, but you can derive them under the assumption that each event is independent, and that all individual, that this individual has a constant detectability over time. And in this case, the key is that you're removing fish when you sample them. So you go out, you might like electrofish, you might do hook and line sampling, you might snorkel count. But the point is that every time you capture one, you remove it or otherwise mark it somehow so that you don't double count it. So if you do that, and you take the log of detection, the log of this formula, it's just a line. So the proportion that you encounter the first pass is the highest, and then it goes down by 1 minus P from that, and then 1 minus P again. And if you plot that in the log, that's a line where the intersect, I guess where it intersects with 1 is just P, and the slope is 1 minus P. And then these blue lines will end up being the simulations of from a Poisson process, the simulations, the number of counts per pass. So in this case, it's certainly possible that, like in this blue line, it had the highest in the first pass, then the lowest the second pass, and then the next highest the third pass. So in that case, it was sort of extremely unlucky in terms of how many it caught the second pass. But as long as you do this with enough different sites, obviously you can fit a regression to this, and so you can start seeing kind of how it would be plausible that it fits this line. Okay. So, any questions about detectability before we get into the stream network part? And then in terms of defining the stream network, it's really just a variant on what we did in, I'm trying to think, what was the first time we looked at unequal distance first order autoregression? Did we do that in the, like, week 3, or did we first do it in week 5? Doesn't remember. 5, okay. So, yeah, thank you. So, essentially what we're gonna do is we're just gonna do the same thing we've always done. We're gonna, well, first there's some bookkeeping, I guess, that's what this slide's about. So, we can take the stream network and we wanna define a directed acyclic graph for this, or a DAG. And, you can do that in, a bunch of different ways, and all of the numberings will give you the same final model. In this case, I'd kind of like to just think about, like, maybe this is the downstream portion, and then you go downstream to upstream. So we start out with node 1. It doesn't have a parent, so we're going to say that it's sort of like an infinite distance from its parent, and that'll, we can talk about that in a second. Node 2, I'm going to number this one, and its parent is the one that's downstream from it. So node 2's parent is node 1, and it's a certain distance. And these are just kind of made up distances that don't correspond to the points. So node 2 would have a parent of node 1, node 3 would have a parent of node 2, node 4 has a parent of node 3, node 5, node 3, and then there's 6, 7, 8 all have 5 as their parent. And it's 8, 9, 10, let's see, 5, 6, 7, 8, 9, 10, 11. So 11, the parent is node 10. So that's all shown in this data frame on the left. So this data frame is sort of a sufficient encoding of the directed acyclic graph for representing the stream distances.
So 11 is the most downstream.
It doesn't, the way I was describing it, I guess 1 was the most downstream and 11 was the most upstream, but, you could have had.
Wouldn't the parent be upstream?
It doesn't, so you can think about it either way. The point is that it won't matter. So, you could also just arbitrarily say this is number 1, or you could say this is number 1, and, well, that's not a good example. I think that you need one of the terminal nodes to be, I guess, the starting node. But it doesn't, aside from that, it doesn't really matter. I guess you can do it any number of ways, but actually you could even just start with this one, and the math would work, but I won't go into that. Yeah, there is in this freshwater community, as John knows, there's sort of, like Jay Verhoof and a bunch of his students have developed these sort of tail up or tail down correlation functions. So, and I always get these mixed up. I think tail down is where, so what I'm going to present is all equivalent to tail down models, whereas tail up is models for like stream chemistry. So you might imagine that that if you're interested in sampling chemistry and the flow goes from stream 11 down, so this is the bottom of the stream network, and these are both headwaters, then this one and this one will be essentially uncorrelated, because if you've got some, this one will just be the mixture of the chemistry from these two. And so there's these sort of tail up models that Jay Verhoof has developed that ends up generating a really complicated correlation structure that represents the physics of streams. We're going to just be looking at these models instead that don't care about whether you're going upstream or downstream, under the assumption that fish can swim upstream or downstream, and they don't really care except about stream distances. So that's sort of a tangent that maybe is relevant to your question, Caitlin. So having defined this directed acyclic graph that represents sort of the stream structure, we're literally just going to sweep, downstream to upstream or upstream to downstream, it doesn't matter, in terms of decomposing joint probability distribution into a series of conditional probability distributions. So that's sort of again, we've been calling that the axiom of conditional probability, that you can always take a joint probability and define it as a series of conditional probability distributions. And let's see. The way to do that is you say that the spatial variable at node S is some function of its parent node. So P of S represents the parent. So like, for instance, node 2, the parent is node 1. And so node 2 here has a mean equal to something related to its parent, node 1. And specifically, it's this function where you've got the value of the parent node times this correlation, this exponential decay function. So kappa is the rate of decay as a function of distance, and d of s is the distance between the parent and the child. So writing it out this way makes it clear that it's sort of it's an exponential correlation function. It's a function of stream distance. And then this formula says that, as you go, well, let's see, if distance equals 0, then this whole thing is e to the 0 or 1. Wait, no. Yeah, so this is, sorry, if this is 0, then yeah, this is 1. So this term is 0, and so the variance is 0 at distance of 0, which makes sense. And as distance goes to infinity, this goes to 0, and so the variance goes to this marginal variance term. So so we've got two parameters in this model. One of them is kappa, the decorrelation rate. The other one is sigma squared, and that's the marginal variance as you go to infinite distance. So that's how we define this sort of conditional structure if you're not starting this chain out, if you're not starting out the graph. If you are starting at the base of the graph, then you just define it equal to, having a prediction of 0, and the variance is equal to the marginal variance of the process, which is what happens if you say that distance equals infinity. So essentially saying that the node 1, which has no parent, is an infinite distance from the nearest node, is equivalent to saying that node should just arise from the marginal or stationary variance of this process. So this is, does anybody recognize these formula? I mean, so we already see that they're sort of an exponential correlation function. We've also seen these formula already somewhere in the class. They're actually just what I defined as the Ornstein-Uhlenbeck process. So, so I think in week 5, I kind of just said that this was the correlation function for this unequal distance time series model for a first order autoregression. And that's equivalent to this, what's called an OU process, or an Ornstein-Uhlenbeck process. Yeah, so essentially it's just it's a way of defining a spatial process on this stream network. And the main restrictions are, I guess, that it's it's an exponential decay by distance. That it doesn't care about whether you're going up or down streams. And that it has to be a directed acyclic graph. So you can't have like complicated estuaries or something in this model, I don't think. At least I haven't tested whether it works in that case.
I have a question about the DAG part of it. So my understanding of DAGs, you can in sort of generalized DAGs, you could have multiple parts that split off and then come together in another node. Can you do that here, where multiple sort of stream paths?
Well, that's the thing. I actually bet you can. That's why I was just thinking that. I bet you could apply this to a braided, like an estuary where streams will branch and then come back together. I just haven't actually tested that case to tested my intuition that it should work that way.
Okay.
Yeah. I've only ever done, totally, they're clearly not.
Yeah.
Clearly acyclic. Yeah, okay, so this is me just writing out the formula, plopping in the mean function and the variance function into this. And so this, I think that, hopefully it makes a certain amount of sense at why it looks like this. I spent a good bit of time trying to find a citation that listed the sparse precision matrix. So, this is defining this process conditionally, or it's like the state space formulation. As we've seen, over and over, it's also nice to have in your pocket the joint covariance. Well, you can assemble the joint covariance function from this, but it's nice to be able to form the precision matrix, the inverse of that, directly, because then that Q matrix is, well, we know it's going to be sparse because this is first order autoregressive. We know it's sparse because, for instance, if we're looking at the spatial variable here and this one, they're conditionally independent, conditional on the value of this one. So the action of node 11 on node 9 is 0, conditional on a fixed value of node 10. And that is equivalent to the concept of partial correlation. So the partial correlation of 11 on 9 is 0, because all that action is through this node 10. So partial correlation is the inverse covariance matrix, the inverse correlation matrix. And so we know similarly that the inverse covariance matrix Q is going to be sparse. It's going to have some zeros. And if we can generate Q, we can plug Q into that GMRF function and compute the PDF of it really efficiently. That's, of course, why the Q has been useful over and over in the class. Okay, so the first thing I wanted to show about this is sort of what I think is kind of a neat trick for at least checking your math on a Q matrix, and we'll get that in a bit. First, we'll just generate this. Here's the encoding of the sufficient description of a stream network, defining it as this directed acyclic graph. If we want, we could look at the distance matrix. Let's see. So the distance. This is defining the distance between each of the 11 points and the adjacent locations. So stream 1, node 1 is only adjacent to node 2. Node 2 is adjacent to 1 and 3. Node 5 is adjacent to node 3. It's upstream node. And then 6, 7, and 8, the three child nodes from that branch point, and so on. And that you can also represent that as a sparse matrix. And then to start out with, we're going to look at the case where we've got only one pass of data, and we're just going to assume the detection probability is kind of infinitely close to 1. Actually, I think I can just set this at 1. It won't mess up the code. So the detection rate per pass is just 1, and there's one pass, so the vector is length 1. And then this is a block of code that just sweeps through the probability of that stream network. So we've got 11 locations that we want to simulate, and I should call that omega v to match with the notation I was using. This doesn't break the code. So omega v is the spatial variable we want to simulate, and if if we're starting at the top node, you know, the node that you're sometimes called like the rooted part of the tree, then the prediction is equal to the mean of that spatial variable is 0, and the standard deviation is equal to this, the marginal variance. And if it's not the rooted node, then the correlation depends on the distance from that child to the parent node, and the standard deviation is this formula, where this is the marginal variance, this is the decay by distance, the increase in variance as you move away, and then taking the square root. So here we've generated, you know, one random draw from this spatial process that's, you know, this exponential correlation function that's equivalent to an Ornstein-Uhlenbeck process. We then simulate the counts for that. Let's see, so where did that go wrong? Oh yeah, oh, I renamed it. So lambda I, in this case, I'm saying that the log, the mean and log space for counts is 4, so that I'm simulating a bunch of counts that are pretty high, and under a Poisson distribution that has a fixed mean variance relationship where the variance equals the mean. If you have a high mean, it means that the coefficient of variation is really low, and so you have kind of more informative data. So I'm just kind of artifactually making sure that my data are really informative, because I only simulated 11 branch points in the network. So this is me just making sure that the model works with this sort of small example. Anyway, so lambda is the prediction of density for each site. And then C sub IZ is the count for each site I and each pass Z. And again, we're only doing one pass. So if we fit this model, well, let's see, in the case that it's only a single pass model, there's a parameter in here called logit detect prob. So this model is set up where you can estimate detection probability, but if you've only got a single pass, it makes sense. Maybe it makes sense intuitively that that you don't have any information to estimate detection probability. We kind of presented this sort of detection probability, something you can estimate if you've got replicated sampling. If you've only got a single pass, you don't have that power. So by default, it's turning off the detection probability estimate. And then I've already compiled it today. So one trick that I thought I would show people, and this is actually how I kind of I kind of had some suspicions about the structure of the Q matrix, but I just couldn't find anywhere that had actually written it out. So I'm kind of embarrassed to say that I spent a little bit of time just kind of basically doing plug and play, kind of like exploring different functional forms within the family that I kind of knew it had to belong to, until I stumbled on the Q matrix structure that actually works. But doing that, I mean, of course, requires that I have some true Q matrix to compare my results against. And the nice thing is that that Q matrix, if you have no data in your model, then the joint negative log likelihood is just equal to the spatial prior distribution. And what that means is that if you compute the Hessian of the inner optimizer, that Hessian is equal to the Q matrix. That's equal to the Q for the spatial process. So in this case, we're just going to see that if you strip out all the data, so if I set all the data equal to NAs, I've got a little, let's see, I've got my standard little piece of code in here that says that if it's this definition of the function is NA, And down where I evaluate the data, I say that if it's not NA, then you deal with, you put the data, the likelihood of the data into the joint negative log likelihood, otherwise you don't. So in this case, if I fix all of the data equal to NAs, the model, the only thing in the joint negative log likelihood is the probability of the spatial process. And the Hessian of the inner optimizer, then is just equal to the Q of that spatial process. So we can extract the Hessian of the inner optimizer without data, and it looks like this. We can also calculate the Q matrix using this analytic formula that I basically worked out from plug and play, given the structure that I knew it had to have. And after kind of an embarrassingly long time, I end up with, an analytic formula that gives the same Q matrix as the as the TMB is doing using this automatic differentiation. So, there's sort of a whole class of math problems that TMB is able to solve that have nothing to do with optimization. One of them is taking sort of, big matrix inversion problems while integrating across random effects. So it's doing that automatically. And as you get better with TMB, I think there's sort of a lot of benefits that you get out of it besides just mixed effects modeling. Okay, so basically this formula is the formula for the analytic formula for the precision matrix in this particular model. I'm not assuming anybody's really going to care about the structure of that Q matrix because I don't think anybody's doing this exact model for their class project. But for people that are interested, it's basically the formula for a conditional autoregressive model or a CAR model. The reason that I couldn't find it written anywhere is that the CAR models I've always seen are either aerial models in which don't deal with distances really, or they're point count models that they're assumed to be equally distanced. So I've never seen this sort of unequal distance point count model. See the Q right now. And then finally, we, just as we always do, we can run the model both ways. Let's see, so opt0 run time, opt1. So, as we often find, well, first I'll just confirm that they give the same answer. So if I run them both, as expected, I get the same answer to, kind of 6 or 8 decimal places for method 1 or method 2, and I can compare the values with the true values from this that I used to simulate the data. So in this particular replicate, the log mean estimate is pretty close, and actually the parameters representing the spatial process are pretty imprecise. I mean, and we can look at what the precision was. Let's see. So like the standard error for log theta was 0.92, so it's not surprising they're 0.6 off. The standard error for log SD is 0.5, and in this case it's like 1.2 off, so that's actually kind of surprisingly far off, but you have to replicate the experiment to figure out if it matters. And the log mean is about almost 2 standard errors away from the true value, which again is a little more off than I would have expected just from our random replicate, but yes, they give the same answer, and they take about the same amount of time to run. The option 2 was using the joint, defining the joint likelihood of that spatial process using the Q matrix that we defined analytically. And so like we've seen several times in the class, that defining the precision matrix ends up being maybe a little bit faster, but it's less than, I mean, it's not even twice as fast defining it from the conditional process. So for my purposes, those timings are basically identical. So any questions about the R code before we look at the CPP code? So, we've got the standard blocks of code at the top, reading and data and parameters. We've got the bookkeeping stuff up here. And so the heart of the code, again, there's this version 0 is identical to the R code that we use to simulate the model. So, well, they're almost identical, except replacing anytime you actually simulate the value with a joint negative log likelihood accumulator. So that's the first version. The second version is defining this Q matrix. So here's some code that Eigen uses. So I don't think I've actually showed you code for how to update values in a sparse matrix using package Eigen. And it's, basically you just start out a sparse matrix Q. And in this case, I then go through and add some stuff on the diagonal where I use this function coefref to just tell it that I want to add in a non-zero value for every element on the diagonal. These sparse matrices are stored internally, I think, in like triplet form. So they've got 3 columns. One is the index of the row, one is the index of the column, and one is the value. And so essentially it's saying that, for row 0 and column 0, I want to put in this value SD merge 1 over the SD merge squared. And then I go through and put in additional pieces. So this is kind of more verbose than the R side because I can't use stuff like row sum and col sum, and I can't do operations on sparse matrices like I can in R. But it is the same formula to get into it. And then once I've assembled that Q matrix, I just plop it into the density GMRF function. And when I call that with Q, it returns a function, and then I use that function immediately on this object called epsilon. Input. So those are the 2 different methods. And then, as always, a mixed effects model needs a block of code that defines the probability of the random effects and then the probability of the data given fixed and random effects. And in that case, this is, we have this log-linked linear predictor. The linear predictor has log mean and just a spatial process. And lambda is that log-linked linear predictor. And then we put in the lambda times this detection per pass to represent the fact that, it's actually a little bit, there's sort of a hidden trick in here. I won't go into it, but in this case, it makes sense that if you've got some density lambda, the first, you can multiply that by the detectability per pass to kind of get approximately how many you expect per site. So anything anybody wants to dig into on the C++ code? We're far enough along that hopefully everybody, except for this how to assemble the Q matrix using that coefref stuff, this all should be code that we've seen several times, so I'm kind of hoping people are fairly familiar with syntax. So I'll just assume that no questions. So finally, the last thing I wanted to demonstrate was that, what happens if you've got multiple passes. And so I'll just close farm and reopen it to use the same random seed. So in this case, CIZ is this 3-column matrix with, the counts in the first pass, the counts in the second pass, and the counts in the third pass for every site, each of these 11 sites. Maybe just for kicks, let's see, so I'll just count it out. So in this stream network, the key to doing this was that I put a node at the join point of every time two streams met each other, any point where there's 3 or more streams connected to it, I'm putting in a node. And so you could imagine that actually node 3 and node 5 don't have any samples, and they're only put into the model to make this directly acyclic graph work. And so I'll just pretend that that site 3 has no data and was put in there for convenience, and site 5 has no data and was put in there for convenience. So now we've got a model that looks like this, and the model is automatically just going to predict in density at site 3 and 5 based on the predictions of the neighbors and the distances. Let's see, so in this case, we can again just confirm that we've got the Q matrix right, and sure enough, the difference between the analytic and this Hessian is vanishingly small. It's like 1 trillion or something. And we can again run the model and compare the true and the estimated values. Let's see. So, oh yeah, okay. So, so let's see. Oh yeah, that's logit scale. So I have to do this Q logit. So in this case, the logit, the probability, the encounter probability for the first pass was 0.5, and so the logit of that is 0, and the logit scale estimator is, like -0.1, and the standard error for that logit prob is 0.12, so it's within a standard error of the true value. And of course you can, just to kind of get into review mode, well in this case, with this one, I don't know why, that putting in the Q matrix was actually a little bit slower. Any speed up that's on the order of 2, your machine's doing other stuff, or my NOAA machine, people are spying on me and doing progress checks and stuff, and so there's a lot of variability in the speed checks. What else? Yeah, okay, so we talked a little bit about bias correction. Does anybody want to review that for a little bit? Like, anybody want to take a stab at summarizing what we said about bias correction? Well, or does anybody remember the term retransformation bias that came up? Well, we only hit on it super briefly, but, basically we've got this logit linked linear predictor for the data. So, for lambda, the density at each site I is equal to this log mean plus this spatial variable and then exponentiating that. And so, long story short, these random effects are thought to be a random variable. I mean, that's the interpretation of a random effect. The model is treating them as a random variable and then integrating across their value to compute the marginal likelihood. And so these random variables, these random effects have some non-zero standard error. They have some variation that the model is integrating across. And so using the delta method or doing a Taylor series expansion, if you take some nonlinear transformation of a random variable, like if you take a random variable A that has a mean mu and you exponentiate it, the mean of that exponentiated random variable is not equal to the e to the mu because of because of the shape of it. So let's see, I can write that, I can kind of draw that on the board. Or I think it's sort of crappy board. So if you've got some random variable that's normally distributed, A, and B equals e to the A, then we know that B will follow a log normal distribution. And the median of this and the mode of this will be equal to, if the mean of A is mu, the mean and the median of this will be e to the mu. But the mean of this log normal distribution is actually not e to the mu anymore. The mean of this is somewhere to the right of that, and we know that from like the bias correction formula for a log normal. People in fisheries talk about that a lot, where the mean of this log normal is e to the mu plus the variance squared, the variance divided by 2. And so if you do a mixed effects model and if you specify a normal distribution for your random effects, and then you want to calculate something as a nonlinear transformation of those random effects, then you have to do this bias correction. You have to add back in the effect that this transformation has on the variance of your random effects. And so geostatisticians have called that retransformation bias, and they use that as an argument for only putting a spatial model, only ever doing spatial models on linear models instead of general linear models. Geostatisticians used to be like, oh, you can't smooth in log space or logit space. You always have to Krieg in natural space. That was sort of the claim for a long time until people started figuring out how to deal with this retransformation bias. So in this case, we can run this model one more time using this built-in feature for bias correction in TMB. Let's see, and all you have to do is tell that bias correct equals true, and then opt1. Let's see. Oh, I get what's happening. Yeah, okay. And then I also have to AD report the lambda I to get bias correction to work. So just a second. recompile it. What I forgot, I wasn't planning on covering this, but we got a little bit of extra time, and bias correction is sort of one of these features that I think people should know coming out of the class, a retransformation bias. So just to summarize what I'm doing, say I want to calculate an unbiased prediction for lambda, the density of fish. That lambda is a nonlinear transformation of a random effect, because in this case it includes the spatial variable, e to the spatial variable. And so to do that retransformation bias correction in TMB, you tell it that you want the variable you want to compute. You pass it as an AB reported variable so that it's going to try to calculate the standard errors of that variable. And then, let's see, so I'll run this. So, and then to look at the output, we can use the summary command. And suddenly there's this new column. So when we've done summary on a standard deviation output of a TMB object, in the past we've just got an estimate and standard error. And in this case, now we have a new column, estimate bias correct. And any observation about this estimate bias correct that anybody has offhand?
Seems to be consistently higher by 1.
Yeah, exactly. So it's always just a little bit higher, and that's a property of that that log linked or that exponentiating process. So exactly like how it works in a log normal distribution, the mean is higher than the median because it's this right skewed function, the distribution. And if you do a Taylor series expansion, you can kind of work out that the impact of bias correction is an increasing function of both the standard error of the random effect and the second derivative of the function you're transforming it with. So the second derivative of an exponential function is positive, the variance is always positive, and so the effect of bias correction in this case is always positive. Yeah. And if you wanted to calculate the standard deviation of this bias correction feature, there's kind of a neat little thing that Casper built where it computes the variance of the parameters, plus it computes the variance of this bias correction algorithm, and outputs a slightly higher standard error after bias correction, typically. Yeah, so that's bias correction. And again, we don't have any data at CIZ. We don't have any data at site 3 or 5, which are these join points. And so it makes sense that these standard errors are a little bit higher for those 2 sites that we don't have any data. But they're still not as high as they would be. They're not the marginal variance. They're not equal to the marginal variance of the process because they're being shrunk towards the estimates at nearby nodes. I guess just one more thing to say about that. Let's see. More. Oh well, not exactly. Oh, whatever. Yeah. So that's bias correction. Any final questions on this, or basically what I was going to suggest as an exercise, if we have time, which we do, is for people to just work individually to try to put in spatial variation in the catchability, the detection probability process. So we've got 20 minutes left. Just as a class, what do you think would be the easiest way to put in, well, how would people try to put in spatial variation and detection probability in this model?
you could do something very similar to what you've done for actual, just catch rates, but then I guess it would have to be in logit space instead of block space because it's 0 to 1.
Totally. Yeah, so specifically, what set of changes were you making?
So I would have then theta, SD, and mean for detection probability instead. And probably simulated a similar way in the R code. And I think there would just need to be 2 cube matrices, one for actual number and then one for detection rates.
Totally, exactly, so, yeah, so you could redefine log theta as the mean of it. You could put in a new parameter vector of, theta deviations for every site. Put in a new component where you increment the joint negative log likelihood. And just for simplicity, we can just assume that it follows the same spatial decorrelation rate as the variation in density. And then it has to be in logit space, so you'd have to, instead of detect probability being the inverse logit transform of the mean, you'd have to have a detect probability that's calculated for every site and change the detection per pass component. So is that enough discussion together for people that want to take a stab at that? Okay, yeah, one nod wins the day. Yeah, so go ahead, I'll just kind of come around in a minute here. And we could meet back at 10:15 to see if anybody finished and what their conclusions were. Yeah, 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 I mean, at least, obviously, you would use the true pass piece that will basically help you start thinking about detectability of the vehicle.
Do we have time today to talk about change in support models or maybe?
Totally, yeah, let's just talk about
there like a really flexible data structure in TMB, like a list in R, where like, because I'm imagining like the most generalizable version of what we're trying to do, where you have like instead of repeating chunks of repeating out like constructing queue,
Yeah.
just like be like, I don't care, this dimension has this many, the queue is this size.
Totally.
Is that possible to do like a?
Yeah, for sure. There's you know, like at the top here, instead of data scalar, data vector,
Mm-hmm.
you can just have something called a data struct. I'm pretty sure.
Oh, okay. I think I saw it. Is that in Vast code?
Yeah, it is in there.
I've been creeping on your Vast code a bunch.
Yeah, I mean, there's, so, yeah, data struct, object. I don't really use it. So I guess, yeah, you have to define this sort of structure as a function at the top of your code, it looks like. It's been a while since I did this, and then extract list elements, their name, so you know, it's like a tagged list the same way.
Mhm.
And then you just pass it the object and the function that defines the structure of it.
Okay, so on the R side, you would basically say this is how many.
I think you just pass it a tagged list, like on the R side, you would just have an object called object, you know, data, quote, object equals any list. And then on the CPP side, you'd have to define the list, the structure of the list in detail. So it's not as flexible as R, where on the R side, it just could be any list and it doesn't really care.
Yeah.
I think it has to do it this way because R, like, you know, when it builds it, it needs to define the memory of it, you know, the memory sizes in some ways, and so it needs to know more about the structure. Yeah, I mean, if I use this, like, that Q, that function of generate the Q matrix from the inputs, I'll probably just try to get Casper to implement it as a function in base TMB. So that, you know, like it's computer science, there's all this discussion of like where a function should live in the stack of dependencies. And, you know, something general like that, we try to push kind of like up the stack into the base TMB code. So is anybody making progress? Or if not, we could, there was one request to talk about change in support models, which would just be kind of a very different direction and very cursory description, hand-wavy description of it. Any preferences?
I'd like to hear about change in support.
Okay, yeah.
Sure.
Okay. Well, maybe, did anybody make any progress they want to talk about, or? It's fine if not, we've only had less than 10 minutes, so. Yeah, okay. Well, so then I'll probably end with the change in support piece. And I should warn you that I didn't, you know, if I actually, well, at some point there's class evals. I think the class evals are being done online this year for this class. And so in theory, I think people should get an email from SAPS to do that. But I'd also love feedback on the structure of the class, and in particular, whether there's sort of topics that are less important that could be phased out and other topics that are more important that should be put in. If I was gonna do something about change in support, I would actually kind of, you know, develop code, and that would help me to train my intuition more. And having never actually built code for it, I'm a little worried that my intuition might be wrong in some small way, but So I think the case that you might think of for change in support, well, does anybody want to like hazard a definition of change in support or cases where they've heard the term? I mean, I know, John, you've talked about this in your spatial stat reading group, I assume.
A bit.
Yeah.
Not much.
Well, my understanding is that you might have, multiple data types. So in this class so far, we've talked about point process models mainly. And then we've talked about, and then we've mentioned that there's aerial models as another data type, but we haven't really done anything with aerial models. And so I'm just trying to draw out a case where you might have, well, this is kind of hard to see in this projector, but some of these are red points and some are black. And you might have sampling data at the red points that's a point count data. So like in a public health case, you might have like, what I guess I understand is called like cluster sampling, where, some rich philanthropy or some other international public health organization comes in and does sampling, like detailed sampling through interviews of people at these randomly chosen locations. And then you might also have, government collected data that's occurring on, statistical areas that the government cares about. So, like in Commonwealth countries, we all have like counties and then cities incorporate. I don't know how it works in France actually in terms of like local policy, but somebody was pointing out actually that Laplace, besides being a brilliant mathematician, he was the first person he was commissioned by the king to do a census of what was the population size of France in like 1800 or something. And so he did it as this tag recapture problem where he like sampled counted how many people he encountered, and then 5 years later recounted, tried to figure out how many, did another sample of the population of France and saw how many of those original people he resampled in the second sample. So governments for a long time have been doing these sort of samples that they collect at these sort of aggregated spatial scales because we need to do that for democracies to figure out voting shares or whatever it is, so, or taxes. And so you might have, samples of the red points of like, fertility, and then at the blue points might be, over the blue areas, you might have some government sample of the total number of births in that county. And so the county level data is an aerial model, where, the data doesn't give you any information about what's happening within that area, whereas the red points are point count data that are, referenced, associated with a particular point in space. And this presentation is all about space, but you could extend this to time as well, or any other, like integral projection models, ecology, kind of do the same trick over other continuous value traits. Okay, so we've got the red points that are point count and the blue areas that are aerial data, and then, we might populate a series of black points that represent random effects that we don't have any data for, so predictive locations. And in reality, we probably want a lot more black points, but I got tired of drawing in paint. And the trick is that, we do exactly what we've been doing for the point count data, where you've got observation, like a Poisson count for the, density function evaluated at that location. But the aerial data, it's less clear what you do with, because of course this area is associated with a big block of the density function. And so, in what we'd like to do ideally is define a density function across the spatial domain and say that the expected value for the observation associated with this blue area here is equal to the integral of that density function over the area represented by that polygon. But of course, that integral across a function is really expensive. I mean, expensive, or you'd have to rely on analytic techniques. And so the kind of way that it's easy to do in a computer is to say that it's equal to the expectation for this blue area is equal to, the mean of the model density for all of the vertices occurring within that polygon. Or if that would be sort of a coarse approximation. If you're doing INLA, the SPDE approach is actually saying that there's some density, this between these 3 points that they're connected with a triangle, it's doing this piecewise linear or like this bivariate interpolation method, and so you can interpolate density to a finer grid within here and take the average of that. But they're all kind of variants on the intuition that to calculate some expectation for some data associated with an area, you take some integral of fine scale locations within that area. So is that, John, do you think that's sort of a fair high level summary?
It's all about scaling.
Yeah.
I think maybe the simplest example I can think of, kriging comes from mining originally. So if you think about like some ore in the ground, you can stick a pin in the ground and say, what's the concentration of the ore right here? You'll have to take some sort of core or something, right? And you can do that a bunch of times and get those samples. And then you want to sort of interpolate what that is inside there, but then you excavate it. Pretend you would put it back after, but you excavate it all and say, what's the total amount of ore in this volume? And then you want to sort of compare those scales from those point estimates, the point observations to the volume observation. It applies the same in area sort of issues and things like that.
Yeah. Yeah, and I mean, there's this whole kind of long literature about how to do change in support, in different instances. But again, now that we have computers and we have efficient techniques for hierarchical modeling, I think basically every change in support problem that I've ever encountered can be fixed or dealt with generically by trying to define some model on a fine spatial scale. And then as long as it's finer than the scale of every observation, you can go from fine scale to coarse scale by doing an integral, or in practice a summation from the fine scale to the scale you're working with. And so then the only real challenge is computationally doing your model at a fine enough scale that all of your data is as coarse or coarser than that. So in the global burden of disease, if people are really trying to take it down to 1 kilometer by 1 kilometer cells, any point count data you can say is just, I guess, that 1 kilometer by 1 kilometer, and then county data or country data is all, coarser scale. So you just sum all of those fine scale grids up to get the expectation, get the moments for that aerial data.
So sort of computationally, if you were doing this in like an inlog example, would your solution to, let's say, combine like aerial and point counts, you want to like make those comparable, be to like for each iteration sort of scatter a bunch of points across the surface and then just do some sort of like population weighted average?
Basically, yeah.
Add like whatever, like super fine mesh nodes, or add the points, the observation points.
Exactly. That in practice, in theory, that's all it is. I don't know that INLA, allows you to do that. I haven't used INLA in a while, so I don't know if there's any way that you can tell it that an observation is the sum across a set of nodes. But of course, in TMB, you can do all the same stuff in INLA and just write the code yourself to say that you've got some, this is some data that's normally distributed around the mean, normally distributed with mean equal to mean of these 4 vertices. So it'd be easy to do in TMB at least. I mean, it'd be easy to write the code in TMB. There's also some identifiability issues that come up when using the loss approximation. So for instance, if all you have is aerial data and you're trying to fit this model, it's possible the inner likelihood will have a likelihood ridge such that the Hessian of the inner optimizer is not invertible. because this one, if all you have is aerial data, this one could be slightly higher and this one could be slightly lower, and the mean would be the same. So I don't really know the identifiability concerns of using the Laplace approximation in TMB to do this. But in TMB, we can use all the stand samplers, and we can do it with MCMC, and that would for sure work. Or I'm pretty sure it's identifiable if you've got a few different locations of point count data in every area. I'm pretty confident that will work using the Laplace approximation.
You said you can combine TMB with STAN, or that would just be a solution, you would just work out in STAN instead?
No, yeah, because there's a package called TMB stan where you just write the you just write the CVP in TMB and then you just all the samplers in stan you apply.
I tried it this weekend. It's like the easiest thing.
Yeah,
to
cool.
run.
Cool.
Yeah, it's really awesome.
Cool. Yeah, it's new. I've never tried it yet. Yeah.
Yeah, it's literally just a TMB stand function and like,
Yeah.
you don't really have to do any prep. You just give it TMB objects.
Cool.
And you're good to go. Cool. That's pretty cool.
Yeah, and of course Stan doesn't have the little, last I checked, Stan didn't have the Laplace approximation. It also doesn't have the sparse matrices, so I do think there's a class of problems where it would be more efficient to build in TMB and then run the Stan samplers, but.
And also, yeah, and it doesn't have a way to do the SPD approximation,
Exactly, yeah.
especially because it doesn't have sparse matrices.
Totally, exactly. Yeah, I mean, I think that Johnny is working on the change in support using the SPD method, and I don't know if he's doing it in TMB or Inla.
I think,
Is he doing it? So they've got some way to do it in Inla then.
I think he's working on it, yeah.
So nobody, maybe, talk with me and I'll refer you to Johnny if you actually start trying to publish on this. I think that my idea for how to deal with this probably in part arises from talking with his professor Jono. So he probably deserves first crack at that publication.
Good to know that it can be done for someone's trying it.
Yeah, totally, yeah. You've got confirmation that it works, but that's secondhand.
Because you said that John Wakefield's working on that, the changing support model maybe?
Yeah, well, I thought Johnny is a Burm student who's working with.
Johnny is a stat student working with Jono.
Yeah. And what's Johnny's last name again?
Page. John Wakefield.
He introduced himself to me as Jono. I don't know.
He did that guest lecture at
Yeah.
516 for us.
But he, like Jono, like,
Jono, yes, that's his preferred nickname, apparently.
I don't know.
I didn't know that.
Yeah. He's the only other person who lives in Capitol Hill, so I see him and his daughter at the paint store all the time. Okay, well, that's it for today. Sorry we ran a little late. As I said, I'll be gone Thursday.